Welcome to our rock unit activity for Geology Lab. This handout has a little bit of background information, and I will be supplementing it with some notes that perhaps you would like to take some notes in addition to what we have in our small little handout here. Of course, last time we did finish up taking a good look at our minerals with some diagnostic physical properties that would help us to identify those. Now we want to continue with Earth materials, the rocks. So what is a rock? Well, a rock is a mixture of one or more minerals, sort of aggregates of minerals. Sometimes can have organic matter with it as well. But this first little portion gives you just some background there. It does talk about the rock cycle, which we will go in much greater depth here in just a few minutes. But let's just take a look at the handout. This is like the first page of the handout. The second page does talk a little bit more about the concept of the rock cycle that James Hutton, he was a gentleman farmer, they called him, back in the 1700s, and he is known as the founder of modern geology. So he is a very important figure in geology, and he did come up with the rock cycle, showing the interrelationships between our three rock types. So here are our three rock types. So igneous rocks, the sedimentary rocks, and then of course the metamorphic rocks. And we'll be looking at each of those within their own turn, but to think of the earth as a cycle. So we have this little recycling symbol here where rock material is really neither created nor destroyed. It's basically recycled, transformed from one rock type to another, and our rock cycle does depict those interrelationships. So we'll be taking a look at that. Then there's one page in here that talks about the Bowen's reaction series, and we will be looking at that a little bit more closely when we talk about our igneous rock group. The method on how we classify has a lot to do with what minerals are in our igneous rocks, and so these should look familiar. Olivine, pyroxene, amphibole, biotite, those plagioclase feldspars, the orthoclase feldspar, muscovite mica, and quartz as well. So we look at the series of what minerals are contained in coming up with the classification of our igneous rocks and the names that we get for our igneous rocks. And so that's all involved with the Bowen's reaction series, so we will go through that with you. Then the next page in the handout is an example of the rock quiz. This is set up very similar to the mineral quiz. If you recall that, this is the actual handout sheet you will have to take your rock quiz when the time comes. And so as you can see, yes, there will be two questions, an A and a B, for each rock that I'll have for you, and this is a practical exam, so you will have to be able to identify specific rocks. And of course we'll have 25 questions, well, 25 specimens with 2 questions for each rock. Included on here is the names of each of the rocks, so you won't have to remember how to spell them, but I do want them spelled correctly. You will have that word bank. And then we've got just 2 categories here. The type of the rock, and I've already mentioned igneous, metamorphic, and sedimentary. and then the textures of our rocks. And so we have several terms that define the texture of our rocks, and we will be going through each of these and letting you know which type of rock has which types of textures and which rocks are associated with each of these textures. So we will go more in depth into that. But that's the actual quiz sheet you would have. And then the last page here is the key, okay, of the tray of rocks samples that we will be using. And so we'll be going through these. I'll probably try to put the rocks on this key so that you can get a look at all of them as if they were in a tray. But yes, we'll be going through each of these and letting you know which belong to which rock type, our igneous, our sedimentary, and our metamorphic rocks, and what texture goes with each rock. So we've got a lot cut out here for us to go through. So we'll go ahead and just get started with this. Here I have a little bit magnified image of the rock cycle. And so just going through this briefly, I know we did and will touch upon this in the lecture course, but just for review. The rock cycle, we typically start down here in the magma category. Just for traditional purposes, we start there where Earth's material has melted, so very, very hot, and it has gone ahead and melted. And so we begin there typically. You can really start anywhere on this, it's a cycle. But we begin here with the molten earth material known as magma. And then this magma, in some ways, it will work its way up towards the top. So here we've got like the land surface here, okay, is what that's categorizing there. It is called magma when it is beneath Earth's surface. When it does come up through a volcanic eruption, it is known as lava, as it is on the Earth's surface. So we do start out traditionally with magma, and then as the magma begins to cool, we call this process crystallization, and the minerals that the rock material, the magma material is composed of will begin to crystallize out, and it does crystallize out in a very methodic order, which we will look at the Bowen's reaction series here in a bit. But it will begin to crystallize out according to how these minerals will solidify, and is very much based on temperature. So that is a crystallization process. Now, if the cooling is beneath the Earth's surface, as you see here, this is known as intrusive. So the cooling that you're going to get beneath Earth's surface is going to be very slow. So you will have some very large mineral grains and crystals that you'll actually be able to pick out each little individual mineral type in these. And these are known as intrusive igneous rocks. Very cool and slow cooling rate, okay, giving large crystals. But let's say, for example, that magma was erupted through volcanism, and we get the lava cooling much more rapidly on Earth's surface. Okay, these are known as extrusive igneous rocks. For these, they're going to have much smaller crystal grain sizes of your minerals. Maybe can't even make them out. They might be so small, the individual minerals. And they could cool so rapidly that perhaps they don't even have time to create mineral crystals. And that would be like a glassy type of a texture. And sometimes they can get trapped gases in their structure and leave little holes behind, little frothy, bubbly looking holy appearance, vesicles. And so leaving that type of texture, those are known as extrusive igneous rocks. Okay, so let's say we have igneous rock, either intrusive or extrusive, and somehow we get uplift and exposure to the Earth's surface to where we can have weathering take place. And weathering can be probably both here. Physical weathering or mechanical weathering, where you physically break down the rock to smaller particles, or perhaps we have chemical weathering, so chemically you're acting on the rock. So whichever case, you are getting the rock to be broken down to smaller particles, and that's known as the process of weathering. So you're getting small sediment sizes, perhaps they're large pieces as well, but it's the breaking down of the rock. So the weathering process occurs, and then they get transported. So transportation, usually by water. Water is a very, very important transportation agent, but it could be by wind to some extent. There'd be very small particles if wind was picking it up. Ice, our glaciers can move tremendous amounts of sediment. So in some means we're transporting our sediments to another location, but eventually those sediments will become deposited. So we get the deposition of the sediments. The water action velocity would slow down, and perhaps then the sediments would fall out, the wind would stop blowing, etc. You'd get some deposition of your sediments. To turn it into a rock, you need this process of lithification. So lithification is the compacting, so the pressing down, compaction, and cementation. So cementation is like gluing our particles together. So usually fluids, it could be a silica-based type fluid. Maybe we get a little iron oxide in there as well. Something that will cement those particles together. That is known as lithification, turning it to stone, lithification. And that is our category of creating a sedimentary rock. So that would be the sedimentary rock type of rocks. After that, let's say we'll continue on, and you can do little shortcuts here, but the sedimentary rock, let's say we take it and let's say it gets buried somehow through plate tectonics, the motion of the Earth's plates, and it gets buried to where it is undergoing some extra heat perhaps, or maybe just pressure, or both, or you could get some chemically active fluids acting on it. All of those are termed metamorphism. So in some way we are changing, metamorphosing our rock, okay, through pressure and through extra heat, but not so much heat that it melts our rock. Okay, we'd be back to magma if it melted. But increasing heat, increasing pressure to the point that it actually changes the arrangement and the alignment of our minerals, our individual mineral crystals contained in our rock. And that's known as metamorphism, so it does change the rock. And it becomes the metamorphic rock type. Now, let's say we have this metamorphic rock that undergoes so much heat and so much pressure that it actually melts the rock once again. So if it does melt it, we go back to a magma and we say our cycle is complete and that we can begin anew. But actually, you can get shortcuts between these. You don't have to go, the rock does not have to go through the entire rock cycle. It can take some shortcuts. Say we started with a sedimentary rock and it got buried and it completely melted. So here we would be starting back with a magma once again, and on our way to creating an igneous rock. Perhaps we have an igneous rock that gets buried and undergoes a little more heat and pressure, changing it up just enough to create a metamorphic rock, but not so much that it melted, right? But back to a metamorphic rock. Or perhaps we have the igneous rock and it does melt again, and then you're creating once again the magma and starting again. So there are all these little shortcuts that it can go through. It doesn't have to go through each one of these to make a complete cycle. But the rock that we hold in our hand today may have had a very different past, because Earth's history is a tremendous amount of time that has passed. 4.6 billion, with a B, billion years of Earth's history. And so the rock you hold today may very well have been quite a different rock in Earth's past. Okay. So that is a little bit about the concept of the rock cycle and how we get the three main rock types here: the igneous rocks, the sedimentary rocks, and our metamorphic rocks. Okay, that was a nice look at the rock cycle. Now we want to move on in actually how do we identify our rocks, putting them in their specific rock types. Well, rock types and individual rock names are determined by describing their textures and their compositions. Texture refers to the shape, the arrangement, and size of mineral grains or the mineral crystals in a rock. Mineral grain size is often used to separate rocks within a particular type. So we'll be looking at these textures, and each rock type, so igneous, metamorphic, sedimentary, each type uses different terms to describe its textures. So we have quite a few texture terminology to go through. The other thing we look at, of course, is the composition, and that refers to the minerals that are found in a rock. So all the minerals we studied, out of those, only about 9 are important in rock formation. So often the larger mineral grains can be identified by sight, by using those physical properties that we studied in the mineral activity. So, and first here we would like to look at the igneous rocks, which, by the way, I'll just mention, are numbers 1 through 13 in our tray. Those are the igneous rocks. But we want to look at the mineral composition first of our igneous rocks. And in order to do that, we have what is called Bowen's reaction series. So I've got that page of the reaction series. You do have this in your handout. But this Bowen's reaction series is used to demonstrate how a single magma can produce rocks of varying mineral content. So N.L. Bowen, he was an early geochemist of the first quarter of the 20th century. He discovered that as magma cooled, he was doing this in a laboratory, took a magma and began to cool it, molten earth material, magma. He realized certain minerals crystallize first at very high temperatures. So you see on our chart here that we do have temperature, not the specifics of it, but that at a very high temperature we still can get some of our minerals to go ahead and crystallize out. And then temperature, as it decreases down the line here to a lower temperature, we get our last mineral to solidify out at much cooler temperatures. Okay, so these minerals listed on here should look familiar, that what we studied, but at successively cooler temperatures, other minerals will begin to crystallize out. Bowen also demonstrated that if a mineral remains in the melt after crystallization, it's going to react with the remaining melt to produce the next mineral in sequence. And so we do get what we call a series. And we see here the calcium plagioclase down to the sodium plagioclase. And you can actually get a variety of minerals through the cooling here, but we've just got the end members, the calcium plagioclase and the sodium plagioclase that we studied in the lab. But then as it continues to cool, we do get the quartz at the very end. So this Bowen's reaction series does show the sequence in which the minerals crystallize from a magma. And you can get very complex magmas. So we still need our minerals out, so we'll grab the minerals to place on the chart here. That sometimes a visual is nice. But the first sample to crystallize out of the magma upon cooling, still at very high temperatures though, is the olivine. So I'm going to go ahead and place olivine right up there. That was number 18 from that tray. Place that mineral high on that temperature chart. The second mineral to crystallize out was the calcium plagioclase feldspar. I'm going to go ahead and place that one right up here. Okay, that was that number 15 from your mineral tray. So we're looking in the mineral tray now, not the rock tray, not just yet. So that one comes out, and as the temperature drops, it's sort of a continuum here, sort of continuous series here, going from the calcium to the sodium. So I'll go ahead and place the sodium plagioclase right down there, that lighter gray one. So a series of, and you can get variations of this would be like 100% calcium plagioclase feldspar, but you can get proportions, a certain percent calcium to a certain percent sodium as we go down this. So they call that a continuous series. And 100% sodium, Na, sodium plagioclase would be this specimen down here. Okay, so that's sort of a continuous one. As that temperature is dropping, we get the sodium-rich plagioclase feldspar. So varying ratios in between. Okay, next the temperature continues to drop, and the olivine is reacting with the remaining melt, and it forms a new chemical composition which becomes the pyrrocene. If you remember that one. There's our pyrrocene. That was 25, number 25 out of your tray. Next, the double chain tetrahedron silicate. If you remember that from lecture, the double chain amphibole. So we'll kind of place amphibole right there. That one was actually number 26. Okay, our amphibole. And next, let's see, the sheet silicate. If you remember that, our sheet biotite mica. I'll put biotite mica off over in this side. Okay, so that's the biotite over here, number 17, running out of room there. Followed then by the feldspar. This one is the orthoclase feldspar. Okay, let me grab that one. That was like number 13 out of your tray. Remember that one. And then the next one down, as temperatures continuing to cool, we have the muscovite mica, another sheet silicate. Okay, right there. The lighter one is the muscovite mica. And then the last one down here, at the coolest temperature, the pure silicon dioxide, the quartz. Remember that one, and I've just got the the glassy quartz there for us. But we had several variety of quartz, if you remember that. So this chart basically involves about 9 minerals approximately, which are important in rock formation. So there are thousands of minerals, but they don't affect the rock formation. So these are the main rock building minerals. And so if we look here at the right side, the headings that we have for these igneous rocks, we're going to see that those words again, intrusive and extrusive, that we introduced to you when we were looking at the rock cycle. If you recall that intrusive forms under the Earth's surface as magma, and extrusive forms on the Earth's surface as lava. And so we'll have a much more rapid cooling rate with a lava at the conditions at Earth's surface versus being beneath Earth's surface. And that was a much slower cooling rate, intrusive. So the way they set up the names here, we look at what we call textures. Are they intrusive or are they extrusive, depending on the cooling rate of our rock. And that's going to give us different textures of our igneous rocks. So just for one quick little example here before we move from this is, let's suppose we had a rock that had a little bit of the olivine, just a little bit of olivine. It was mostly the pyrocene and had a trace of the amphibole in it. And it was mostly calcium-rich plagioclase. So that's sort of its mineralogy here, kind of in this region. Okay, so we've got 2 choices for our igneous names here. One is called gabbro, and one is called basalt. And you also have the scoria here as well. But intrusive would be what we call gabbro. It's the same mineralogy. And I'll go ahead and put that out for you here. That's, I believe, number 6. I just dropped it on the floor. 1 second. Just lost gabbro. Okay. Here's gabbro. Found it. Okay, so gabbro, so that same mineralogy in there, a little bit of olivine, the pyrocene, trace of amphibole, and mostly this calcium plagioclase. So don't know how well that's showing up, but intrusive. So this cooled, all those minerals with that mineralogy cooled slowly, and so we do have, it's very dark, right, because these are all very dark minerals, becomes the dark gabbro for the intrusive igneous rock name. But if we have that same mineralogy, that same composition of minerals, but yet this cools much more rapidly, so now we're talking some sort of volcanism, lava at Earth's surface cooled much more rapidly. Now we have, this would be number 8 in your tray, the basalt. Okay, again, a very dark mineral because of that dark mineralogy that it has. But really, you would have a very hard time seeing the individual crystals in this one. These are much larger, a little slower cooling rate, so you can kind of pick out some of those crystals, individual mineral crystals in this sample, which we would call a gabbro. Same mineralogy, but very fine textured crystals, very fine grained. So that's called basalt. Now, a special case here of scoria would be, we have the same mineralogy, right? But the cooling happened to where a bunch of gases bubbled out of our lava, leaving some kind of frozen bubbles behind where it becomes kind of holy looking. And so that one here, number 12 from your trays, would be a scoria. This is the black scoria. And there's little vesicles in here. I don't know how well those are showing up on this screen, but little black, little small vesicles or holes in there. So we call that vesicular for the texture, and we give it a little bit different name called scoria. So you can see how with our igneous rocks you could have the same mineralogy, okay, but we give them different igneous rock names according to their textures. So texture becomes very important in getting our igneous rock names. Okay, mineralogy is important, that's one part of it, but then the texture is also important, and that's how we come up with our names for our igneous rocks. Continuing on down there, we got a couple other names. One is diorite. The other one is, there's actually misspelled there, that should be andesite. So here we have more of an intermediate mineralogy. So we've got a little biotite in there, a little bit more on the end of the sodium plagioclase, maybe a tiny bit of amphibole in there, just a tad of amphibole in there. But again, because of our textures, if it's intrusive, okay, cooled at a little slower rate. This actually is exhibiting two different cooling rates. We've got larger crystals and smaller crystals. So we'll talk about specifically what that texture is here in a minute. But the other one then would be, I'm sorry, this is the andesite. Scoot that over a little bit. Couple textures there. Here is the diorite. The diorite has the larger crystals in it. Okay, get that name. Here's our diorite. Larger crystals in it. Still fairly dark mineral, in that we still do have some pretty dark mineralogy in there, a little bit lighter with the sodium plagioclase. Here, this andesite would have been very small crystals, even though we do have big ones in here. We'll talk about this special texture where it actually had two cooling rates. It still is extrusive because it was erupted through volcanism, quickly got to the surface, but it probably started cooling beneath Earth's surface, so it created a little bit larger crystal size and finished its cooling on Earth's surface, so it cooled a little faster. So it has two cooling rates happening in our particular andesite. So the diorite, if it was intrusive, slow cooling, versus an andesite, a much more rapid cooling. But again, the mineralogy is the same, but the cooling rates are what differ. And so that gives them a different rock name. So there's the diorite, okay, and andesite. But an intermediate mineralogy, we say. Now down here, this is interesting, we have our granite, okay, which would have more of the orthoclase, we'll have muscovite mica in it, and quartz in it. So if you have this mineralogy, okay, so the orthoclase, the muscovite mica, the quartz, and sometimes you can even have smoky quartz, we call that the intrusive one that cools very slowly. We call that a granite. You might be able to even make out the individual, well, definitely right here is a piece of mica. I don't know how well you can see that. Large mica grain in there. The biotite's kind of in there reflecting. The pinkish is the orthoclase feldspar in these. So that's a granite. Now, the reason the cyanite's kind of off over in the corner there is the granite, or the cyanite does not have the quartz in it. Okay, so it's very similar to the mineralogy of granite, but cyanite, I'll go ahead and put our number 4 cyanite just right there beside the cyanite. And it is lacking the quartz, okay, and the granite does have the quartz in it, must have the quartz in it to be called a granite. Okay, but that cooling is very slow, so you get the larger crystal grains in there. Over on this side then, same mineralogy as our granite, but cooled very rapidly. Okay, this is called rhyolite. It'd be number 7 in your tray, the rhyolite. You do see kind of the pinkish color, like the orthoclase there. A few little specks, they're very small, of the darker kind of a little bit of muscovite in there, that little bit of dark in there. A few specks here and there. Can't really make out any individual crystals on these. So that was a very fast cooling rate, okay, to give it small mineral crystal sizes. But we would call that a rhyolite. Now, the pumice and the obsidian do have the similar mineralogy as the granites or the rhyolite, but because of their cooling history, we call them something a little different. The pumice, again, similar to what happened with scoria up here with the vesicles and the holes in it, we call pumice. It is vesicular. It does have little frothy holes in it because of those trapped gases. So there's a little sample of some pumice. Okay, same mineralogy though, but because of the vesicles, we call it pumice. And then the obsidian. Obsidian has a similar mineralogy as well, but it cooled so fast. So a violent volcanic eruption cooled instantaneously to the point that the mineral grains didn't even have time to create a crystal in their lattice structure. And so we call that obsidian. That's a very glassy structure to it, a texture to it. So we call that obsidian. So as you can see here from our chart, depending on the mineralogy, okay, what minerals solidified out or crystallized out, and how quickly. So what was the cooling rate? Intrusive is much slower, extrusive much more rapid. Some of these have some trapped gas bubbles in it, so vesicular. Some of them were so quick that didn't even have a chance to create crystals, and that would be like an obsidian. So you can see how we get our varying igneous rock names based on, yes, mineral composition, but even more importantly is the texture, okay, the cooling rate, okay, for our igneous rocks. So that brings us then to looking at those textures for our igneous rocks. Okay, so here I have some notes for you. These are not necessarily in your handout, so I'm going to go ahead and just try to place them right over there. Maybe I'll scroll up a little bit here. Okay, so in looking at our igneous rocks, this, of course, if you remember from our rock cycle, this is magma. It's cool slowly, and you'll form very large crystals. The slower the cooling, the larger the crystal, right? The faster the cooling, the smaller the crystals. So we want to take a look at the types of textures for igneous rocks. Remember, I did say that each type of rock will have their own terminology for their textures. And so for this one, we are referring to the igneous rock textures. Okay. So the first one there, the phaneritic. Okay. Phaneritic is coarse-grained texture. This forms when the magma cools very slowly inside Earth's interior. So remember that term, intrusive. Okay. So phaneritic. What we can look at for phaneritic in your trays, let's see. Here's that chart. In your trays, And I'll try to set all the rocks out on there here in a second. But for the igneous rocks, these are going to be numbers, I think I mentioned this before, 1 through 13 are your igneous rocks. Okay, so for rock type, igneous rocks, numbers 1 through 13 are your igneous rocks. Well, the samples that exhibit phaneritic texture are 1 through 6, and we already looked at a few of these. So there's 2 granite samples actually. We have a granite 1 and a granite 2. The first granite sample doesn't have quite as large of particles in it, mineral crystals in it. Granite 2 has much larger crystal sizes in it. So we can say that granite 1 cooled a lot faster than granite 2 because granite 2 has larger crystals, mineral crystals in it. So yeah, we'll take a look at those in a second. Syenite, we have 2 varieties of syenite, a dark and a light sample of syenite. I think your lighter variety is number 3 and your darker one's number 4. Diorite, if you recall, that was an intermediate mineralogy, and diorite, definitely you can see crystal grains in that. The gabbro, remember that one, that's got more of the olivine, the pyrrhocene, a little bit of amphibole in it, so gabbro. And then rhyolite, similar to a granite, but yet it's 1 through 6. No, rhyolite is a different texture. So 1 through 6 have the phaneritic, meaning coarse-grained textures. Okay. Phaneritic. Okay. So 1 through 6 in your tray exhibit phaneritic texture. Okay. The next texture type is the aphanitic, meaning fine-grained texture. This is going to form when lava cools on or very near Earth's surface. So a little bit more rapid cooling is happening with an aphanitic, and so that's going to give you a finer crystal size to your minerals in it. So that then would be your number 7 and 8 in your trays. So number 7 rhyolite and number 8 basalt. So if you remember, the granite was the larger phaneritic texture and rhyolite is the aphanitic or finer grain texture. They had very similar mineralogy, chemical composition, but because of their cooling rates, it changes their texture, and so we have a different name for them, granite versus a rhyolite. And the basalt, if you remember, we had that next to the gabbro, same mineralogy as gabbro, but gabbro has a larger crystal grain, so it's phaneritic. Basalt is aphanitic. So 7 and 8, rhyolite and basalt, exhibit an aphanitic texture. Okay, fine grained. Okay, now number 3, I did mention that when we had a sample in there. Porphyritic. This is 2 very contrasting sizes of crystals. They're caused by magma having 2 different cooling rates, and so it may start out cooling very slowly beneath Earth's surface, doing its thing, creating a little bit larger crystal sizes, but then maybe all of a sudden a violent eruption, volcanic eruption, and it's tossed to Earth's surface, and it finishes out its cooling at a much rapid rate, and we end up with some very fine-grained texture mixed in with larger grains. So that one with 2 contrasting sizes of crystals is called porphyritic, The only one that we have that is porphyritic is the number 13 in your tray, andesite, and it is andesite with that E in there, andesite. Okay, so that one is porphyritic texture. Okay, next one there, we mentioned this one before, glassy. So glassy texture, there's no mineral crystals developed whatsoever. It cooled at such an extremely rapid cooling rate, definitely extrusive there, cooling rate, that the mineral crystals didn't even get a chance to start forming. Okay, so it's very smooth texture to it. It's called glassy. And the only one we have in our tray with a glassy texture is the obsidian, your number 9 obsidian. Okay. And there is one more here, vesicular. I mentioned that a couple times. Now for this one, it's cooling. When it is cooling, gases are bubbling through, trying to escape and leaving these little holes. So it may produce a frothy or a holy appearance to it, and we call those vesicles, little circles, little vesicles in it. And you have 3 in your tray that do exhibit the vesicular texture, and so that would be the number 10 pumice. We showed you that one. The number 11 and 12, your scorias. You have 2 scorias. We had the red variety that is number 11, and the number 12 variety is black scoria. So it's a little bit different. This red one has maybe a little contamination of some iron oxide, something a little rusty in it, that created that beautiful red color to it. So those are your textures for your igneous rocks. Okay, there are 5 different textures for the igneous rocks. So I want to go ahead and place those rocks. See if I can remove them from here. Get my rocks and move this out of the way real quick. Owens reaction series, so that you can see the igneous rocks placed on the key here and match up kind of a name with the sample. Okay, so the first granite that you have, your number 1 in your tray, has, versus let's say our number 2 in our tray, these are both granites. Okay, and the granites have different cooling rates, clearly. I was looking for a magnifying glass. I couldn't quite find it. But you can still pick out the texture in there, the grains, okay, in this one. You can see individual mineral crystals in this one, but let me tell you, this number 2, you can really make them out. You've got your feldspar right there, the orthoclase. You can see the little flecks of mica in here. So this is very coarse grain. They're both coarse grained, but that one's a lot larger. And so, of course, our granite 2 here would have cooled at a much slower rate than our granite 1. Okay. Both, though, are intrusive, so they both cooled at slower rates than, say, an extrusive one. But this one cooled much more slowly here. Okay. We've got a light and a dark variety of our cyanites. So again, just within certain ranges of mineralogy, you'll get slight differences in the appearance of these. Oh, I'm covering that up a little bit. But the cyanite, okay, for number 4. So that's a lighter version with a little bit different mineralogy, slightly, and then a darker syenite. And then the diorite, number 5. This is sort of an intermediate mineralogy. Okay, but again, a coarse-grained, so that's definitely a phaneritic texture. And our number 6 gabbro, right there. Number 6 gabbro. Okay. And if you recall that 1 through 6 in our trays are exhibiting the phaneritic, the coarse-grained textures. Okay, igneous rocks, but coarse-grained. Okay, and number 7, the rhyolite. And number 8, the basalt. Okay, these two exhibit the aphanitic or fine-grained texture. You will need to know these textures. Okay, so 7 and 8 exhibit aphanitic textures. See the word basalt there. Okay, then we have the obsidian, number 9. Okay, the obsidian. Very smooth, kind of a conchoidal type of a fracture, the way those break. This is a glassy texture, obsidian. Okay, obsidian exhibits a glassy texture. That was the only one that had the glassy texture. And then remember we had 3 that exhibited the vesicular texture. So the number 10 pumice. And we had a red variety of scoria, right there, number 11. And then the black variety of scoria, number 12. And those exhibit vesicles in them. So these are vesicular. 10, 11, and 12 exhibit the vesicular texture. And then we had just one here, andesite, number 13, that exhibited the porphyritic texture. Crystal sizes, 2 very contrasting crystal sizes because of having 2 different rates of cooling. So the andesite number 13, you can make out those larger, sort of lighter colored crystals. That was a very slow cooling rate beneath Earth's surface, and then it got extruded volcanism, and then it finished its cooling much more rapidly, giving it very, very small, very fine-grained, the darker mineral in there, andesite, so porphyritic. Okay, so once again, 1 through 6 are your phaneritic textures. 7 and 8, the aphanitic textures. Okay, 9, the obsidian is a glassy texture. 10, 11, and 12 are the vesicular textures, and number 13, andesite, is the porphyritic, 2 contrasting size textures. So those are the synopsis of our igneous rocks. 1 through 13 are our igneous type rock. So type would be igneous rock. And then the variety of textures that go along with our igneous rocks. Make sure that you learn those terms: phaneritic, aphanitic, porphyritic, glassy, and vesicular. Associate those with igneous rocks, okay? And then make sure you know which rock, okay, has which texture, because you could be asked the type, these are all igneous, and the texture. So know your texture names for your igneous rocks and study those, okay? And again, coming to class and actually handling these rocks, seeing the details of them, that's going to be a big plus. Okay, those were the igneous rocks. Okay, let's continue on and take a look at our sedimentary rocks. And the sedimentary rocks are numbers 14 through 20 in our trays. So let me show you that real quick in our trays. Okay, so number 14 starting with conglomerate and going through number 20 bituminous coal. Okay, so again we have our type, which is the sedimentary rocks. And if you recall, the sedimentary rocks are formed through the process of weathering, and the weathering can be in the form of mechanical weathering, where you're physically breaking down the particles to smaller sizes, or can be chemical, so derived by solution dissolving into water. Water's our main weathering agent, and then carried away to another location, and then that's free to deposit out or precipitate out of the water. So chemical derivation is one way, and a mechanical weathering is another way. So we do want to look at what the textures are for the sedimentary rock group. Okay, so starting off, the textures for what we call detrital are consisting of mineral grains or rock fragments derived from that mechanical weathering, so the physical breakup of rocks. And this is numerous ways. Again, water does play a big role through frost wedging. The freezing and thawing cycle of water can do a good number on breaking down the rock. Sheeting, or we call this exfoliation, where the rock is sloughing off because it expands, it contracts through the heating and the cooling of a day and can slough off. That's one way. Biological activity, so the burrowing of animals, the roots of plants can act to physically break up our rocks. So then they get transported. Remember that they could be transported through water, that's the main one. Wind can transport sediment, as well as ice. Remember that and recall that from our rock cycle. And then they get deposited as solid particles. So the identification of our detrital sedimentary rocks are going to be due to this size of the grains or the fragments. And we've got 4 size categories. We really only have 3 mineral samples, but we put all those sizes in there for you. But the mineral composition is of secondary concern. So for our detrital textures, we focus mainly in on particle size, okay, sediment size. And so we have this first one here, conglomerate, and that ends up being the name of your rock, okay, and it's gravel-sized particles, and it's just greater than 2 millimeters. I mean, they can be really large. They could be cobble or boulder-sized particles, but they have to be at least greater than 2 millimeters in size, so they're fairly large particles, can be, and that's known as a conglomerate. Okay, I'll just set that there. That's our number 14 in our trays. Goes by the name conglomerate. So that is how we get our name of our sedimentary rock, is due to the sediment size. Okay, so that's conglomerate, gravel sized. Then we have the sandstone, so our sand size particles, 2 millimeters to 1/16 of a millimeter. So these are fairly small sand-sized particles. We actually have 2 varieties in some of the trays. Some of the trays we have a red color sandstone. Okay, so I've got an example of the red, and these are gritty feeling. They'll feel gritty. That's a good way to try to identify them. But we also have a grade variety, and so as these are becoming sedimentary rocks, recall that you have to have the lithification process where you have cementation or the gluing together of those little particles, and so the colorations are stemming from what type of glue or cement is joining those particle sizes. So with the gray colored sandstone, the cement is more of a silica or a silicon dioxide cement, and with the red you're getting more of an iron oxide cement, so sort of that rusty red color is what's gluing all those little sand-sized particles together to create the rock sandstone. Okay, so some of the trays have red, some of the trays have gray, and so you will want to make sure that you can distinguish and identify these both as sandstone, because either one or maybe both could be on the rock quiz. Okay, and then let's see, we have the shale sized. Okay, these are silt or clay sized particles. I got a size on there, less than 1/16 of a millimeter in size. Okay, and so your number 16 in your trays would be a good example of the shale. So that's what we call it, shale. So very small sized particles. Your number 16 shale. Now the siltstone is very small, so less than 1/256 of a millimeter. Can't get all that on there. Of a millimeter. Very, very fine grained clay-sized particles. We don't have an example of the siltstone in our trays, and you seldom see a pure siltstone in nature, but they do exist. So we've got some nice examples there. 14 is our conglomerate, 15 is the sandstone, and 16 is the shale. Okay, and those are the names of our rocks that exhibit a detrital texture. Okay, detrital. So that's one way, by looking at the particle size to get a texture for sedimentary rocks. The other way is to look at, bring that down, those that are formed through chemical weathering. Okay, these are derived from material that gets carried in solution and ends up in lakes and seas and out in the ocean, later precipitated by either a biochemical, meaning animals or organisms are secreting these as shells, something like that, and or inorganic, just a chemical reaction or a physical process such as maybe evaporating the water portion off. These are known as chemical weathering, and so we would call it a chemical texture. So for these, the mineral composition is the primary consideration in the identification of the chemical sedimentary rocks. So we got to kind of think about our minerals when we do think about these. So one type that we have here is stemming from the chemical mineralogy of the calcite. So maybe I'll just set our calcite from our mineral trays. That's coming from the mineral tray, not the rock tray. That was number 11. So calcium carbonate, if you remember, calcite is calcium carbonate, and so it would fizz and react with acid. Okay, and that's the main component in limestone. So your number 17 limestone in your tray, okay, comes from the mineral calcite. Okay, so limestone number 17 is a chemical sedimentary rock. And then if you remember our mineral quartz, okay, the silicon dioxide, that's our mineral glassy quartz there. That was that number 21, glassy quartz. That is the main makeup of our chert. So silicon dioxide chert, so number 18 in your tray, stems from the chemical quartz or silicon dioxide. So number 18 chert is a chemical sedimentary rock. And then number 3 there, clay, so aluminum oxide. If you remember kaolinite, okay, the kaolinite was 29 from our mineral trays. It is an aluminum oxide type of a silicate mineral. Okay, that's the main ingredient in our bauxite. Okay, so number 19, bauxite, okay, in your trays. Bauxite is Arkansas's state rock, right? And so this is the main ingredient. There are several other aluminum oxide minerals that also go into making our bauxites, but kaolinite is one of those. But number 19, bauxite, is a chemical sedimentary rock. Okay, make room for our last one down here. So now you can get, if the chemical kind of orientation of it is altered plant fragments, we can end up with our bituminous coal. Okay, so I don't have any altered plant fragments there, but bituminous coal, so organic matter. That would be number 20 in your trays, the bituminous coal. So these are chemical sedimentary rocks. The limestone, number 17, chert, number 18, bauxite, number 19, and 20, bituminous coal. All chemical, okay, sedimentary rocks. So there are basically two textures for the sedimentary rocks. All right, these minerals out of the way. All right, so the detrital, you only have two choices for the sedimentary rock textures. One is detrital and the other is chemical. Okay, but you see how we got our names from those sizes there and from the chemical content. Okay, all right, so let's go ahead and put those in our little key here so we can get a chance to see all of those side by side. So there's our conglomerate. Number 14, number 15, we had two. We had the red or the gray. Not sure what you'll have in your tray, but you'll want to rotate trays around. Make sure you examine several different trays of these samples because they can have variations in them, and you need to be as familiar as you can with your rocks. And so the more samples you look at of the same rock, the better you'll be able to identify them when the test time comes. So number 16 is our shale. Okay. And then the limestone, number 17. And the chert, number 18. Okay. Bauxite, number 19. Notice how bauxite and conglomerate look fairly similar, but conglomerate will actually have little pebbly pieces in them that you can see. These are more of little voids or holes kind of in the bauxite. So that's one way you can try to distinguish those. And then the bituminous coal, number 20. Okay, these are your sedimentary rocks. The first Three here are the detrital texture. So conglomerate, sandstone, and shale are detrital textures. And then these here, 17, 18, 19, and 20 are the chemical sedimentary rocks. So chemical texture, limestone, chert, bauxite, and bituminous coal. So two varieties of textures there. You do want to make sure you know and can tell those textures apart because you could be asked the texture for these. Okay, so those are the sedimentary rocks and their types. Okay, let's continue and let's take a look at our last rock type, the metamorphic rocks. With the metamorphic rocks, if you recall from our rock cycle, we could take any other rock. It could be previously an igneous, a sedimentary, or another metamorphic rock. We call it the parent rock. And they undergo the process of metamorphism. So we add any combination here of increasing the heat, but not to the point of melting. Recall that. Perhaps we increase the pressure and or activity of chemical fluids on our rock during that process of metamorphism to create an offspring, our product, metamorphic rock. So there's only two textural divisions that provide the basis for identification of our metamorphic rocks. The first one is called foliated and the second one non-foliated. But real quick here, just to make sure we know which are the metamorphic rocks in our trays. Those are going to be, starting here with number 21, the slate. All of these ending with the anthracite coal, number 26. So 21 through 26 in your trays are the metamorphic rock types. Okay, so in looking a little closer at those textures, our first texture here is termed foliated. So what's happening here as the heat and the pressure begin to get increased, it will act on our minerals in our crystals here and recrystallize them with what they say a preferred orientation. So an alignment of our mineral crystals will change, and essentially they are perpendicular to the direction of the compressional force, so that added pressure. The resulting mineral alignment usually gives the rock a layered or even a banded appearance, and we term that foliated texture. So what I'm going to start with, let's say we began here with our, this is the shale, which is a, oh, there we go, let's get that in the view. The shale, which is, recall that that is a detrital sedimentary rock. So let's say we begin with that sedimentary rock, shale, number 16 from your tray, and have that undergo metamorphism. So we're going to increase the heat and the pressure just a little bit on that. Okay, so there are different degrees of metamorphism. But you add a little more heat, a little more pressure maybe, and it transforms those little mica minerals that are in that shale and creates the slate, the number 21 slate. Okay, we call that slate, and that's the metamorphic rock slate. Okay. And if we continue with heat and pressure, so we're going to a more moderate degree of metamorphism, we have here, we get a little bit a growing in size of those mica crystals, mineral crystals. We also have in this number 22 called schist, we have little pieces of garnet in the schist that you could make out. I'm not sure if you can see it from there. Maybe this magnification might help a little bit. But there are little pieces of garnet, the mineral garnet in there as well, and a little bit larger grains of the mica. But they're all aligning in sort of a layered kind of look to it. But that would be with some moderate heat and pressure. We call that schist. And then if you continued and you really squeezed it and a lot of pressure on it and more heat, you'll get what we call gneiss. It begins with a G. We'll get the spelling of it here in just a second, but this is it is a very nice rock, but that is pronounced nice. And you can see it does have this banding appearance to it, almost striped looked, banded appearance they call that, where your light and your dark minerals that were in your rock actually separated and had a preferred orientation here. So it does look banded. And that is a very high level of metamorphism to get the banding like that. But that's nice. So 21, 22, 23 in your trays are metamorphic rocks that exhibit the foliated texture. Okay. And the second texture of our metamorphic rocks is called non-foliated. So for these, no foliation, no banding or preferred alignment happens during metamorphism, but the rock consists of only one mineral and it forms sort of this equidimensional crystal. So it's pretty uniform crystals. Sometimes the crystals look kind of fused together because of that extra heat and pressure. So when we talk about the non-foliated textures of our metamorphic rocks, we always talk about the parent rock. So what was the rock to begin with, and then how did it look and become as an offspring. So when we start out with the parent rock of the chemical, get that all on there, chemical sedimentary rock of limestone, which is number 17 in your trays, the metamorphic offspring would be number 24, marble. Okay, so you do kind of see the crystals look a little more enlarged and a little more fused in the metamorphic offspring of a limestone. So the mineral composition is that calcite. If you remember, our limestone is made of the calcite mineral. So that calcite mineral more or less gets recrystallized and then has this equidimensional fused kind of look in the marble. As it recrystallized, it got a little bit larger and formed the marble. Okay. Another example of the non-foliated texture is if, say, we started with a quartz sandstone. So I've got here my quartz sandstone, the red variety, and we increased the heat, increased the pressure on that, metamorphosed that sandstone, and it would become the offspring. The metamorphic offspring would be our number 25 quartzite. It might not be showing real well here, but if you were able to take a really good look at it, those crystals, those grains do look kind of fused. So a quartz or even a chert, something with a silicon dioxide or a silica type mineral in it would create a quartzite. And you can get different colorations of quartzite as well. It can be quite beautiful. Another sample we have is, let's say we started with the parent rock being the bituminous coal. Okay, so our number 20 bituminous coal and we undergo more heat, more pressure. So as coal, if you go deeper and deeper into the ground, it's under more pressure, more heat, and it will really fuse those altered plant fragments of the bituminous coal, right, that chemical sedimentary rock there, into our number 26, the anthracite coal. And one good way to tell the anthracite coal from the bituminous coal, because they're kind of similar looking, is the anthracite coal. You have to play with it in the light, but the anthracite coal has sort of a yellow or goldish kind of a sheen to it that the bituminous coal doesn't have, and that is one excellent way to tell those two rocks apart. So the sedimentary, sort of the parent rock, and then the metamorphic offspring would be the anthracite coal, our number 26 in your trays. So these all exhibit then a non-foliated texture. They don't have any preferred alignment of the crystals, the mineral crystals, so they're sort of equidimensional crystals. Okay, that's termed non-foliated for our metamorphic rocks. Okay, so I do want to put these in the little key trays so that you can see those kind of side by side. Okay. There is the slate number 21, and slate does come in a variety of colors, but I will be sticking with this green colored slate in all of our trays and on the test, okay, so that you can easily tell it from the shale, which will all be the black variety of shale. Okay, and number 23, nice. That's pronounced nice. Okay, so we've got the slate number 21. This would be just sort of a low-grade metamorphism to get a slate. Increasing heat pressure, you're getting moderate metamorphism with the schist. And then, let's just squeeze the schist out of it, right? And we'll get this nice rock here. You'll see the banding. It's a high grade of metamorphism there, kind of a play on words there. Nice rock. And again, these are all foliated. Okay, then we have the non-foliated variety, number 24, the marble. Okay, and that is the offspring of the limestone, right? Metamorphic offspring of limestone. The quartzite, number 25, non-foliated. That's the metamorphic offspring of a quartz, or a quartz sandstone, or even a chert, since it does have silicon dioxide as well, the quartz in it. And then the anthracite coal, that is the metamorphic offspring of the bituminous coal. Okay, so all of these are the metamorphic, 21 through 26 are the metamorphic type rock. That would be their type. Their textures then are either foliated, 21 through 23, or non-foliated, 24 through 26. Okay? All right, and that kind of concludes the going through the rock types and the textures. And do recall that there are variations in the textures for each rock type. So you do want to be familiar with each of the rock types' textures. Okay? Okay, so to conclude, I want to briefly go over what you can expect on the rock quiz, the rock exam. So what I've done here is I have placed all of the rocks for you on the key in order, so they're all numbered. Remember, on the rock quiz they will not have the little numbers on them, so you do want to spend some time being able to identify your rocks by name, know what type they are. So are they igneous, sedimentary, or metamorphic? And what is their texture? Okay, so the rock quiz, like I mentioned before, will be a sheet like this. And as promised, the names will be listed. So we have all of our names, okay, on there. Now, if it is a scoria, let's say, you don't really have to say red or black, but we had two varieties of the scoria. Remember, the sandstone has two varieties, the gray and the red on there. Your cyanites, you had a light and a dark cyanite, but you can just call it cyanite. That's fine. So the names will be on there. So remember, I might ask you the name, but I might not ask you the name. So you do want to resist automatically putting the name down. But it's set up similar to the way the mineral quiz was set up, where we would have a little box with a number on it. So here I've got 13, 14, and 15, which would correspond to numbers 13, 14, and 15 on your quiz. And so there are a question A and a question B, and you would put the answer to question A on the appropriate line and B on the appropriate line. So that's a little test-taking skill there that you have to make sure you can do that. But here's kind of what I could ask you. Yes, I could ask you the name, but I could ask you the type, right? So if the question is asking the type, then it's one of these three. It's igneous, metamorphic, or sedimentary. Or I could ask you the texture, right? And so if I ask you the texture, it is coming from all those textures that we studied. So they're listed here. They're not in any particular order. I think they're alphabetical here. But as far as which ones are igneous textures, which ones go with sedimentary texture, and which ones go with metamorphic textures. And so that you do need to work out. Make sure that you do know which type of rock has which types of textures. Okay. So for example, let me just select a couple rocks here and see if we can't come up with some answers for these. Let's see. Let's just do like this, I suppose. So in a sense, it's similar to the mineral quiz, except you don't have quite as many things to keep up with. It's just name, type, or texture, right, that I could ask you on these, not all those physical properties like we did with the minerals. So a little less things to have to keep up with. So and again, these little numbers are not going to be on them, so you do have to know these and be able to recognize them. Okay, so for our question 13, let's say I have this rock in here, and question A on 13 is asking for the name. So do you recall what the name of this is? This is gabbro. And then the B question for number 13 is the type. So do you remember gabbro's type? What type of rock is it? It is an igneous rock, if you recall. So we would put in slot A for number 13. Here we go. Put that in real quick. A is the name, so we put gabbro on that line, and the question for B was the type, and so you'd put igneous for that. Just got to make sure you put everything on the correct lines. Okay, so now for number 14, it did not ask the name, so you have to resist writing the name down. You've got to know what the name of it is, you know, to figure out its type and its texture, but you want to resist writing that name down automatically. I have to ask you for it. So 14A is asking the type. So first of all, what is this? Okay. And you'd have to examine it and come up with limestone for that. Okay. So what is the type of rock that limestone is? Limestone is a sedimentary rock. And for B, question B is asking, well, what is the texture of that rock? So it's sedimentary, but it is a chemical sedimentary rock. So you do have to recall the textures, right? So they're listed on here, but you do have to know which goes to which. Okay, so it would be a chemical, okay, sedimentary rock. So line 14 was asking for the type, not the name, the type, which was sedimentary, and the texture would be the chemical. And that would be your answers on line 14, okay, for those. So see, we didn't ask the name at all on that one, but you had to know what it was to be able to come up with the other things. So you see how that works. And on this last one here, we've got the name. So we do want the name. And if you look at that one, it does have that yellow goldish sheen to it. So that's an easy way to distinguish the anthracite coal from the bituminous coal, let's say. So this is the anthracite coal, would be the name. What was the texture? So my goodness, what was the texture of the anthracite coal? Well, anthracite coal is a metamorphic rock, and of those types of textures, we had the foliated and the non-foliated. So the anthracite coal is the non-foliated variety. Okay, so we would say anthracite coal and non-foliated for your line 15 on your test, right? So line 15, anthracite coal and non-foliated would be your answers. So you do have the types listed, you have the textures listed, but you got to know which textures go to which type of rock, right? So being able to identify and give the name when asked of your rock, what is its type, what is its texture. So that's quite a bit of work you have cut out for yourself to learn a lot about your rock types and the details of those textures. Okay, so that's I'm giving you an idea of how we would do the rock quiz. Okay, and so do spend time, and I highly recommend looking at several trays of minerals because there are little variations to them. Also remember that we had the red variety of sandstone as well as the gray. You could get either one of those in your on your exam of that as well. So okay, and as always, if you have any questions about your rocks or any concerns, make sure that you do get with me, and have fun with these, and good luck with your rocks.